Here I'm going to look at limits of functions with a particular view on moving on to calculus and looking at differentiation by first principles. But to start with, I'm going to recap some of the functions I looked at in a previous video. So let's have a look at the linear function first. That means it's a function of a straight line, i.e. when I put in different values of x, I get a definite value of y. So if I increase x in that direction, y seems to increase here. And if I decrease x here, y just seems to decrease. But for every x value, there's a definitive y value. Now, if I look at the next function, which is my quadratic here, if I increase x in that direction, I'm getting particular values of y. Okay, so here, for this value of x, I get that value of y. For this value of x, I get that value of y, and so forth. So these values of y are negative, and then when I go here, I just get a positive value of y whenever I put in x, but I still get a definitive value of y whenever I put in x for this particular function. Same if I move in this direction. For every value of x that I have, I just get a different value of y. Then if I move on to the cubic function here, when x increases in that direction, all that happens is I get a certain value of y for every value of x. And that value of y can either be positive or negative depending on the value of x that I started with. Likewise, if I move x out in this direction, I get another positive or negative value of y, but I do get a definitive value of y for that particular function. The next one I'm going to look at is one of the last ones I looked at in the previous video, which is an exponential function. So what happens to the value of y when x is actually a power? So what I'm going to do is I'm going to look at a particular function, f of x equal to, with a being 1 and b being a half to the power of x. So that means for every value of y, I just need to take the number half and then put it to the power of whatever value of x I want. Now, I looked at that in a previous video, and the sketch of the graph looks something like this. So when x was negative in this direction, okay, we had quite a large value for y. For example, if x is minus 4, then f of x, so if x equals minus 4, f of x then just becomes half to the power of minus 4, which is the same as, if we look at our indices, that's the same as 2 to the power of 4. 2 to the power of 4 is 16, so y would be very high. But if I look at x is equal to 2, the value of y gets quite small. So the value of y here, if x is 2, that's going to be 1 to the power of 2, which is 1, over 2 to the power of 2, which is 4, so that's just going to be a quarter. Then if I increase x again, so when x is 10, f of x is just going to be a half to the power of 10, which is 1 over 2 to the power of 10, which is a very small number. 1 over 2 to the power of 10 is 1 over 1024. So, if you want to think about that in indice form, that's just going to be 9.7 by 10 to the minus 4. So it's going to be 0.00097. Okay, so it's going to be a really, really small number. So just for space here, I'm going to move things around. I'm going to bring this over here. Bring that there. We knew that was when x was 10, so let's have a look and see what happens when x is even bigger. Let's say x is 100 this time. So when x is 100, f of x becomes 1 over 2 to the power of 100. Which actually becomes something like 7.9 by 10 to the minus 31. Okay, so an incredibly small number as x is getting bigger. But what we'll notice is if I keep on increasing x, let's say I make x 1,000 to 1,000,000, okay, all that happens is the value of y gets smaller and smaller and smaller, and it approaches another number. It seems like it's getting closer and closer to 0, but without actually touching 0. So what we say in that fact is that this function never actually hits 0, but gets as close as possible to 0 without actually touching it. And that's how we define a limit effectively. So if you think of a limit in normal terms like a speed limit is something, let's say you've got 120 kilometers an hour. Well, that means that is the maximum speed that you can go. So you can drive as fast as that, you can't go over that speed. In maths, a limit is a number that a certain value approaches or gets as close as possible to without actually touching it. And most of the time what happens is the value that our function is approaching is undefined for that particular function. So we're just going to write down what the definition of a limit is to start with. That's certainly just a definition that we can work with and allow us to understand the definition, and it has a peculiar way to write it, but this is something you're going to get used to for working with limits later on. So the definition of a limit, we write it as lim here. X goes to a. That means as our value for x approaches a here, the limit of the function f of x, i.e. the y value, goes towards this number L. Okay, so the number L is the value that our function approaches as x approaches a. So if you think about this function up here, that one there, we saw that the function f of x equals to 1/2 to the power of x. As x got bigger and bigger, so let's say as x approached infinity, the function got closer and closer to 0. So the limit of that function is 0 as x approaches infinity. There's a few different ways to work with limits. For any of the functions above, for example, it's usually the case that you simply plug in the value for x and that gives you a corresponding y value. And there isn't a limit for these particular functions so long as we don't have x being a denominator. The problem with x being a denominator is that if you have a denominator of 0, we know that that number can't exist. So that's an undefined number, so therefore we'd have to use a limit for that process. So in a lot of limits questions that you come across, we're dealing with questions that have x as a denominator. The reason for that is as that denominator comes close to 0, we have to use a limit. So for the most cases, if you're asked to evaluate a limit for as x approaches a certain number, you can just plug in that number that x approaches and you get the corresponding value of y. So if you want to look at the limit of any particular function, like limit as x approaches 0, let's have a look at what happens to this function. We could say it's 3x plus 4. Well, as x approaches 0, the limit of that function here would just be 3 times 0 plus 4, which is 4. Because that's a linear function, it just means that when x approaches 0, the function gets closer and closer to the number 4. Turns out when x is 0, the function gives you a value of 4. So there's no real need to work with a limit there because there's nothing that's undefined. As x gets closer to 0, the y value just becomes 4. What happens sometimes is if you have a function like this, x squared minus 1 over x minus 1, and you want to see, well, what happens to that function? What happens to its y value as x gets closer and closer to 1? Well, let's say we're putting 1 in for x. You simply just get this 1 squared minus 1 over 1 minus 1, which is just 0 over 0. Now, because we can't determine what that value is, that's called the indeterminate form. I.e. there's no value like that exists, 0 over 0. It's undefined. Remember, any number over 0 isn't a real number, so it's an undefined value. So therefore, that doesn't exist. So we don't know what's happening to our function here as x is closer and closer to 1. So we have to use a different trick. And the trick really is to just factorize it if you can, and then you divide by the common factors if they exist. So what we'll do in this case is, well, x squared minus 1 is just the difference of two squares. So that factorizes to x minus 1 times x plus 1, because x squared minus 1 here is just the difference of two squares, x squared minus 1 squared. So rewritten, that's what this becomes. The limit as x goes to 1 of x minus 1 over x plus 1. Well, these just divide in. So the actual limit for this function, if I was to draw it up, as x gets closer to 1, it's just going to be 1 plus 1, because we're just left with, just rewrite that, x goes to 1. So the limit of that function is just 1 plus 1, which is 2. So I know that as x gets closer and closer to 1, the y value gets closer to 2. We're going to look at another type of function now, and a very common one that's going to crop up. We can look at, well, what happens to the function f of x equals to 1 over x, or x to any power, that is. So I'm just going to move that out of the way, and we're going to look at the function f of x equals 1 over x. Well, let's have a look. When x is 1, y just equals 1, or f of x equals 1, because it's just 1 over 1. When x is equal to 10, f of x equals 1 over 10, which is 0.1. Likewise, if x is equal to 1000, f of x just becomes 1 over 1000, which becomes 0.001. I can keep on increasing x, and x can get larger and larger and larger, but I know what's happening here to this function is that the y value is getting closer and closer to 0, because if I have x being any number other than 0, okay, and x is continually increasing, then the y value is getting closer and closer to 0. So what I know is that the limit as x gets bigger and bigger and bigger, i.e. goes towards infinity, of the function 1 over x, the limit of that is equal to 0. That basically means if you have a function, and if I just want to plot just the points that I have here, well, when x is 1, y was 1. When x was 10, y was 0.1. When x was 1000, so way further down here. So that function here is just approaching 0, but without actually taking the value of 0. Likewise, we can say that, that's the case for any value, x power of n, or even if I just put like a constant here, if that's a constant, some constant c, so some number c, if I've got x to the power of n, well, the limit of that is 0, because the function will never touch 0. There's a few tricks to dealing with functions to find the limits of functions, that is. Quite often, if you've got a function with a denominator and a numerator, so a fraction, as x gets closer and closer to infinity, for any kind of example, let's say 2x squared plus 3x divided by, let's say, x squared plus 3. Okay, if you're dealing with that function, this peculiar function, you're asked to find the limit of this as x gets larger and larger and larger. Well, we introduce something called the dominant term. The dominant term is there because it's the one that's going to dominate as x gets larger and larger and larger. And the one that dominates is the one that has the highest power of x. So in this particular function, it's x squared. If the highest power of x was x cubed, then that will be the one that dominates. And whenever you have a dominant term like that, you divide every term in the function by the dominant term, i.e. the highest power of x. And that allows you to get the limit fairly easily. Okay, so you divide the top and bottom by the dominant term. In this case, the dominant term here is x squared, so I'm going to divide everything by x squared. So this limit then becomes, as x approaches infinity, 2x squared over x squared plus 3x over x squared, all divided by x squared over x squared plus 3 over x squared. Now what I'm going to do is I'm just going to rewrite that. That's the limit as x approaches infinity of, well, 2x squared over x squared is just 2, and 3x over x squared is just 3 times 1 over x, or 3 over x. X squared over x squared is 1, and 3 over x squared is just 3 times 1 over x squared. And if we're trying to evaluate that limit, if I looked above, you can see that the limit as x goes towards infinity of any function with x to a certain power being the denominator is 0. So that is just, to evaluate those limits now, that's just going to be 2 plus 0 over 1 plus 0, which is just the number 2. So I know that this function gets closer and closer to 2 as x approaches infinity. I brought this in initially at the very start of the video, talking about what happens to certain exponential functions, so I'm not going to spend too much time on it. We saw that here, as x got bigger and bigger and bigger, that function approached 0. So what we can now write is the fact that the limit of any function as x goes towards infinity, and that function is some number a, okay, times some number b to the power of x, is going to be 0, so long as b is a fraction between 1 and minus 1. Okay, that function has a limit, and that is 0. Okay, so I've looked at limits of functions there, and we've seen for certain functions, okay, a limit is defined as a value that our function gets close to as our x number or value approaches another number. For example, for some of them, if x approaches infinity, our function approached 0. And that's what a limit is, okay? Just this definition here. That is, our function f of x will approach some number L as x goes towards another number, like that. Okay, I'll be using this when I look at calculus and differentiation by first principles.